if you allow yourself to throw away something of lower rank,
Right.
you can always find an iterated vibration for each of the fibers. Okay. So if you want to study the structure of a general differential algebraic variety, there are two steps. One would be to understand each of these fibers, and then also to understand how the vibrations are put together. So the second part is basically differential Galois theory. And the first part is the study of the...
It's kind of a joint on Helder.
Yeah. Okay, so you have plenty of these kind of regular sets exist. So, and also just by this delta type minimality thing, there's an easy lemma that if x is regular, then there exists some y which is delta type minimal, which is in correspondence. Where correspondence again means zero dimensional. So from the point of view of studying the structure of these things, if you're only interested in this coarse question about the local modularity or triviality, you can replace x with something which is delta type minimal, and now you have differential algebra, everything that Kolchin did to help you study these things. Okay, good. Well, we got one of these delta type minimal things. Where does the group come from? Well, it comes from differentiating. Okay, so you basically just look at you'd like to basically just look at the tangent space. That doesn't quite work, but that's more or less works. So if x is not locally modular, then there exists this family, of curves living inside of x squared. It follows, and this takes a little bit of work, is that you can actually take the dimension
cross B.
Cross B, yes, this over B. You can take the family. Well, the way that we defined it, we said it's going to have dimension greater than or equal to 2. So theorem, you can actually take it to be whatever dimension you like. So you can take it to be quite large. And by taking it quite large, you can arrange that all of these curves pass through some fixed points inside of here. Okay, so going from 2 to something larger, that takes work, but it's work which is generally done just using the theory of regular types. And so you can get a large family of curves all passing through a reasonably generic points. You have this AB inside of there, and they all pass through here. I shouldn't say AB, it's called CB. They all pass through here. Okay. Now, why do I want to look at all these guys passing through one point? Because you can now look at the tangent space at the point. Or, well, really arc space is what you really have to do.
Yeah.
Okay. So they all pass through one point.
Right.
And so if they're different, and they are because this is a high dimensional family, where family really means that you get different sets from different points, maybe their first derivatives are the same, maybe their second derivatives are the same.
Right.
Maybe up through 5 billion they're the same, but eventually they have to separate.
Right.
Okay? So eventually, when you look at the arcs of these guys, they separate. And so you get the family of arcs of these things at that point. This gives you a family in the arc space of x plus x at that point. And the arc space is not a group, which this is the kind of thing this is a mistake that people make, and people includes us.
It's mistakes are in print.
Not these ones. No. No, we've corrected those mistakes. Okay, but so we're used to thinking that the tangent space you can think of. There are many ways to think of the tangent space. You can think of it as derivations on the on the ring of functions.
Right.
You can think of it as the local ring of functions. You can think of it as the dual number valued points of the variety thought of in the right kind of schemy sense. And that second way of thinking about it is the same as thinking about the first arc space of the variety at that point. So obviously,
Right.
this works when you go to the second arc space, but it doesn't. Okay? The second arc space is not a group in general, okay? Although it's fibered by the tangents, by the tangent space. So the second arc space over the first arc space has principal homogeneous space for the tangent space. Okay? Go to the third one, and the third one over the second one is principal homogeneous space with tangent space over the second arc space. But it's not the case that even though it's this nice affine space structure, that is a group structure, okay, which is really annoying. But don't let that bother you, okay? Because we come back to think about what I was saying, how, well, maybe, okay, we really like to do this with tangent space. Like to separate them in tangent space. Maybe all of the derivatives of this first derivative are the same. Well, if they're all the same, then look at the fibers over that in the next arc space. That is a fiber bundle for the tangent space. Well, maybe they're all the same. So go to the third one. Well, eventually, when you get to the first one where you went from n to n plus 1, where they differ, you really are looking at a family of subvarieties of some tangent space, some fixed tangent space. So you really get out of this, after taking appropriate fibers, something living inside of the tangent space of X. At this point. That's the point. You have this family of subgroups there. And that family of subgroups is parametrized by B. And B...
Yeah, but there might now be a lot more coincidences now.
Oh, yeah. So when I say tangent space, I really, like I said, it's really not the tangent space. It's a fixed choice of principal homogeneous space with tangent space.
No, but I meant your collection B might now be much smaller now.
Yeah, yes.
The equivalence relation
You
is
do have to argue that the dimension, well, it could be, but it won't be. Okay, so what you have to prove is that if these really are different, then the arc spaces are also all different at some finite level. Like they're all different, completely different at some finite level. Right. Yeah, so you eventually get this family of subgroups parametrized by B. And B is morally some power of X. Right? It lives inside of some power of X. Via that parametrization, you get a correspondence between B and the way you're parametrizing these groups. You parameterize groups living inside of an arc space, and so they're also parameterized by that group. Okay, that gives you a correspondence between X and this Kolchin tangent space kind of thing. Okay, so that's a very compressed argument. It's not I wouldn't consider that a correct argument. Well, that is the correct way it's done, but it's not like a full and complete argument. But the the interesting additive group that you get is essentially the tangent space of the non-linear equation that you started with. Okay. All right. Okay. So now,
didn't you say it was an additive group?
Yeah. So it lives inside of. Okay. So this is a tangent space, and now you have to argue that because it's this unipotent differential algebraic group, commutative differential algebraic group, that you can embed it in the additive group, and that takes a little bit. It's an argument, but it's so the way that it's presented, it's an abstract differential algebraic group, but then you have to push it down into an additive group. Okay. All right. So you probably did.
Yeah, probably for the tangents.
For the tangent spaces, he must have done this.
He did it for the tangent.
Okay. Looks like you choose a
In
basis.
general, I think that's not known. Commutative differential algebraic group can be embedded in GA to the N.
So what did we prove? Did we just do it for the tangent space, or did we do it in general?
I don't know.
Don't remember.
Okay, so we gave a proof.
Tangent,
Yeah, so we gave a proof in this case. And I
Yeah.
don't remember whether we did it only in the tangent space or whether it was
Yeah.
in the general case.
Yeah.
So, all right. So maybe I'll end with questions and suggestions for. Well, there are a lot of questions already at the beginning, but questions and suggestions for where this what one might do with this. So the first, so question one, well, is the trichotomy conjecture itself. So I guess it's now a dichotomy for additive groups. And let me just suggest why that might be related, why we might have some tools to get somewhere with it, and where you might want to go. So we have some additive groups as defined by linear PDEs, and you had some family of curves inside of G squared plus 2n. So this is a regular additive group. You can assume that all the fibers themselves are groups. And the reason is basically the same argument I just gave. You can differentiate. Okay, so if you had a family of subvarieties, an interesting family of subvarieties, the tangent spaces will also give you an interesting, well, maybe some iterated arc space, but give you an interesting family of subvarieties with arc space groups. And here, so the beautiful thing that for additive groups, the arc space is a group. Okay? So it's the arc space, it is a group. Yeah, it's just nice. Okay, so it takes groups to groups, and it'll take additive groups basically to
yeah, as opposed to for variety.
Yeah. So if you have one of these guys, you'd want to show, well, you can't have it with high dimension. And one would hope, maybe somehow by differentiating this whole picture, you could convert it into some kind of situation where you had everything was additive, and then you could argue something was horribly wrong. So I'm waving my hands here because that kind of argument, as far as I can tell, doesn't really work, but only doesn't work for me. I mean, it's not going to work for you. Right? So this is a situation where it seems that by pushing a bit more of the linearization technique, somebody who's cleverer than I could actually show that you can't have interesting high-dimensional families of groups. Okay, so the question here is, would linearization further?
So, but you didn't. Can you first state your dichotomy, because I'm kind of a bit lost what you were doing now.
So the dichotomy is, I have a regular additive group, either is locally modular, so it would be like the heat equation, or it admits a dominant linear differential map onto a constant field.
Is it not possible that in this context of additive subgroups that other case could just be like a 5-dimensional vector space over some constant field?
I think
that would be too strong.
Yeah, I think that's too strong. I think you can twist it. There are ways you can twist it. So you can hide the fact that it's a finite dimensional vector space over the constants. I mean, it's morally.
Yeah.
It's morally a one-dimensional. I mean, what it should be is more of a one-dimensional space over constants.
Right.
But I think there are ways you can hide that by conjugating this one. But you're right. I guess that's a possibility. I don't. Off the top of my head, I can't give you an example where that happens, but I think it can happen. Yeah. So the dichotomy is you have G, GA regular. Then G is locally modular. This is conjecture, I guess. Or there exists a space of derivations and dominant linear differential map G to constants.
So, Tom, I mean, maybe I missed it. Is it known that every regular field is
Yes.
Yeah.
Yes, we know every field, and they all are the ones I just wrote down. And that's
all the fields period.
and I guess Phyllis proved this basically,
Why?
but no, she doesn't know she did. So this isn't so much thesis. You worked this out. That every field,
Oh, yes.
What the definable fields are.
every interpretable field is one of these. Is one of these guys.
What kind of map is that?
It's a linear differential.
And what's the kernel?
The kernel will be small. It'll be
Just lower type?
just lower type. Well, lower internal dimension.
Oh,
Which may not be
oh,
seen.
no, your dimension. Yeah, that's okay then.
But if you want to assume delta type minimal, that's what we care to make, assume lower type.
Because G is strongly connected in the sense.
G is strongly connected. G is necessarily
Can't map
strongly
it
connected.
Homomorphically onto anything with lower type
Yeah.
in the differential sense.
Yeah, so the type of this guy would have to be the same as the type of. That's a conjecture.
Oh, I see.
And the suggestion for how one might try to prove it is by with further linearization help. So a counterexample to local modularity is given by such a family, where you could assume that the individual curves, the subsets of G cross G, are groups. You have a family of groups. And well, we try to linearize the total space somehow, and use that to produce this map of all the way. That's for you to figure out. Okay.
Is the linearization process written down anywhere?
Yeah.
Oh, it is.
Yeah. So it's in our paper.
It's in your paper.
It's in our paper. It's basically just take dark space. I mean, that's essentially what I mean by the linearization
Just
process.
once.
Well, you might have to do it many times. And
Yeah.
Take fibers. Okay, so that's question one, and the other questions, which I guess I've asked there, would be: are there further provably locally modular groups? I mean, are there other techniques that you could use beyond the case of two derivations? So, well, maybe I'll just put it this way: what are the locally modular groups? And what I mean by that is, can you give some reasonably concrete criterion so that you can check, if I hand you some linear PDEs, that it defines a locally modular group? Even if it's not an if and only if. It'd be nice if you could give me an if and only if. And this is supposed to help you give, the conjecture is supposed to be the if and only if part. But even if there were just sufficient conditions. So Sonat gave some, but they really only apply in the case of two derivations and one PD.
Yeah.
If you take three derivations and do the same thing, make two of them essentially dependent on the third one? Like one of them is refused and the other is...
Yeah, that should work. Yeah, that works the same. So like I was saying, basically the way that his technique works is, what you show is that if you have some additive subgroup, then its module of differential linear homomorphisms, differential linear characters, is a finite rank module over a ring of differential operators in some smaller number of derivations. Where the number of derivations is, I guess, the differential type of the group. So if your group has differential type 1, then you can just do it with 1. And that ring, it's a left principal ideal domain, so you can start doing things. It's much easier to do the algebra. 2, and then you have 2, and then you have to deal with like serious linear PDEs.
Are all of his examples, do all of his examples have typical delta dimension bigger than 1?
Yes.
Yeah, okay.
Yeah. So so one criterion he has is that
Yeah, typical.
if you're regular and typical dimension bigger than 1, then you are orthogonal to all fields.
Non-orthogonal.
Orthogonal. Typical dimension bigger than 1.
Yeah.
Oh, sorry,
Yeah.
bigger than 1.
Bigger than
I thought
1.
you were saying equal.
Then you're orthogonal to fields.
Yeah.
So that's a way that you can produce interesting examples.
So, then,
Oh, that's
is it true that if you're regular, if you're regular
if you're regular and your typical dimension is bigger than 1, yes, that's true. Yeah, that's included. Yeah, so that's not only in the 2 case.
Yeah.
So that is a sufficient condition, an interesting and useful sufficient condition. Okay, so I think I'll stop there.
More questions? Let me make a couple quick announcements. I think a lot of us are interested.